Hi everyone. So we're going to be discussing the introduction to automation with PLC. All right. So we have gone through this before, maybe or maybe not. So if it's your first time, let's enjoy this. So we're going to start with an introduction to the PLC, introduction to the programming. So our agenda for this video, we probably won't be able to cover all of it, but we will try. We want to go for what is the do more hardware, the difference between syncing and sourcing, an overview of the do more software, and we might be able to go into our first PLC project. Then after that, continuation video will be made for the and or and logic mix, combination of logic, and the timer instruction. Then we'll go for another hands-on example. But for this introductory video, we will at least cover up to the I/O wiring for our first PLC project. Maybe we'll go further and do the PLC program. And next class, we'll be testing our PLC project and simulating. It's very important to learn how to do the simulation, use the Do More simulator in order to understand how to use it, especially because you be simulating a lot before taking out to the PLC. It's rarely that you just don't simulate in an environment where it's not dangerous. You want to make sure that the project actually works before you take it out there. So the PLC that we'll be using, there are different manufacturers. In our case, we're going to use Automation Direct Do More PLC. Major PLC vendors are Allen Bradley, Siemens, Automation Direct, Modicon. There's different types of PLCs out there with different products inside of those brands. For example, the Allen Bradley brand has the Control Logic Slick 500, has the Compact Logics. Automation Direct has the Productivity PLC, but it also has a BRX PLC, which is the one we'll be using. So notice that our PLC is named BRX. It's not Do More, it's named BRX, right? But we will use the Do More Designer software to program the PLC. The PLC side would be this one marked red. This is my PLC. It's very important to note that that's your PLC. Notice that I got here and it says Ys, and the Ys are for the outputs. So the Ys are for the outputs. The X are for the inputs. Okay. If you look closely over here, you're gonna have something called WX0 and WY0 in the W section. We'll be discussing those later on, but just so you know, the W stands for the analog I/O in the Do More, just in layman's terms. So we said before that the X's are the inputs, right, for the PLC, and the Y's are the outputs. But these are what we call discrete I/O. This discrete I/O is either on or off. It does not carry an actual value. On the analog side, we have WX0 will be your analog input, and YX0 will be your analog output. Okay? Nope. It's very important, those concepts. So analog values are values that are numerical. It's not just an on, off, 1 or 0, which this might be represented like this. Also, when you have 24 volts DC, might also be represented that way. So on the analog, you might have a value, let's say a you might have pressure values that range in 0 to 2000 psi. For those who are interested in the mechanical engineering side, this value is very important. The pressure. You might have temperatures that range in 0 to some other value, let's say 1000 Fahrenheit. So basically, those are examples of analog. So on the analog output side, let's say you might probably want to open a valve. You want to open a valve to let flow out. So the symbol of flow, usually it's Q, flow of water, right? Flow of H2O. And you want to open this valve to 50%. So 50% will, instead of on off, opening 100%, which is this, or 0%, you want to open it 50%. So you send a signal that is proportional to the opening and close of the valve. So those are analogs, right? So all these are analogs. We are not covering this yet. We will, but we will cover discrete inputs and outputs. So going back to the PLC, we got over here external power to the PLC. We apply power to the PLC. We also have terminal blocks here for your outputs. And then you got your terminal blocks over here for your inputs. Okay. This right here, this side over here, this is your actual CPU. This is a removable, or you may say replaceable or exchangeable NPU. I'm sorry, not NPU, port for additional communication functionalities. Okay. So, for example, right now you can see we have Ethernet, right? You have Ethernet, but you may also have USB connection. You may have serial connection. So those of you that have seen old phones, not cell phones, but landlines, serial is similar to your phone jack. Your Ethernet is similar to what you plug into the internet. You also have a RS-232 and RS or RS-485. You can select it via software. So the wire it's the same, but on the software, the way the protocol that it uses to communicate, it's different. Basically, just imagine a PLC can talk different languages, right? For example, we can talk Portuguese, English, French, Spanish. So in this, you might say RS-232 is similar to Spanish and RS-485 is similar to English. The way that it communicates is different, right? So, but we still speak with our mouth, right? We still speak with the same port. You just got to select the type of port that you want to talk to. So going back to that, you can also, if it says expansion ports, you can add modules for more IOs in here, like this, and you just connect them to that port right there, and they physically electrically connect to the PLC to add more IO points. So you can add up to 32 point, so 8 with 32 IOs each for an additional 250 additional IO. So that's a lot of IO. Right now, our PLC handles the amount of IO shown there. This is the PLC we will use in class, and it's very important to get to know it. For example, if you build your own company, you might want to put your label of the company right here, and just to distinguish yourself. So whenever they have a problem with the machine, hey, that's not built by Automation Direct. You actually did the programming. Automation Direct does the PLC functionality, does the PLC program, but the person that actually programs it, it is you. You might be wondering here, since it's a robotics class built in high-speed I/O. So high-speed I/O are used for servo motors with encoders. So encoders, since they throw many pulses per minute, I believe we could discuss scan time. So scan times on a high-speed I/O are a lot faster, and they get scanned a lot faster than regular I/O. So instead of being on the millisecond range, it might be on the microsecond range. Okay. Also, this PLC has the versatility that it does not use RAM. RAM. You probably want to Google this term, RAM. RAM stands for Random Access Memory, and it doesn't store the ladder logic in RAM. The good thing about not doing that is that, first of all, it's random access memory, right? So when you power off RAM or you take power out, so if I take this power out, we will lose your programming. Okay? This PLC right here uses an EEPROM, or so erasable programmable read-only memory. That's what EEPROM stands for. So it actually hard codes the program inside the hardware. So when you power it off, it's not volatile, and you will not, I repeat, you will not lose your program. For our class, we will use this port right here, convert it to USB, and we will program using that port. Then we will switch every now and then to RS-232 to another port called RS-232. No. To communicate and power our HMI. So if there's any doubts or questions, please write them down over. I'm going to give you a few minutes here so we can talk more about it. About the analog, don't worry about it right now. Just understand it that there are analog values that you can program in them, and you can control them as well. Not all the time is going to be on or off. For the purpose of this class, and maybe throughout almost the entire class, we might discuss analog at the end, but not right now. Okay. Now we're going to talk about how to wire the PLC, right? So this part that says MPU, consider that just like your I/O or your PLC. So microprocessor unit, they might have other names for it, but basically you're interfacing with your PLC, right? So this is your PLC point or PLC. Let me see how to explain this, right? So you saw this, it has an X value right here, right? Let's start with the inputs. X5, X0. So that X0 is a point. That's a physical I/O point. So this right here will be your physical input point. So just imagine this is X0 right here, right? So notice that I'm applying the positive voltage on this side, and the PLC is providing that path back to 0 volts DC. How does it do it? It does it through the switch. It doesn't mean that it's going to connect. It doesn't mean that I'm doing a 24 volts DC cable straight to a 0 volts DC. That right here, it is known as a short circuit, and that could definitely damage any power source. So if I do that, that's damaging my power supply. Notice that they have a little symbol here. That symbol here is an electronic device here that doesn't permit this to happen. So just take that into consideration, right? So this is your start switch, and it's called syncing because I'm syncing my higher voltage. It syncs down to your lower voltage. So it syncs down to your PLC. Or you can also say that the current goes from the positive to the negative, right? So current will go from the positive to the negative. And the symbol for current, or the letter that they use for current, is I. And V is for voltage, right? So it's always going to go from positive to negative. So in this case, it goes like this, from the positive back to the negative side, right? This is a positive, and this is the, over here completes to the common, to the negative side. Notice that you can also configure them sourcing. In our specific PLC, and the configuration most used in the industry for inputs is going to be syncing. We typically tend to visualize syncing devices a lot better. So if you think about sourcing, now sourcing, the common is providing 24 volts DC, and the current is provided to the device, to the switch. Okay, so once you close that switch, then it completes the circuit. This is hardly used, but it could be used. It could be used. Some people use them due to some configuration issue. They have configured like that, and that's the way they have it. The same thing with syncing sourcing outputs. Most of the industry uses sourcing outputs. Our PLC uses sourcing outputs. Notice that now the PLC, all right, the PLC has 24 volts connected to it. And just imagine there's a little contact here. That when the logic tells this to turn on, the program turns on, this closes, and it provides voltage to the load. The load, well, they're going to call it load to any device that you want to turn on, right? Any device I want to control or turn on. Could be a relay. Examples. I think we already discussed some examples, but it could be a relay. Could be a light bulb, a light, a buzzer. Usually, we will not connect motors directly to the PLC because motors draw high current, and you will only have on our PLC, you will have 24 volts DC available and 0.5 amps per point. So if I were to ask you, Y0, what is the voltage that Y0 can provide, and what is the current? Well, it's going to provide 24 volts DC and at a maximum of 0.5 amps. So if they tell you, we need to control a motor, a DC motor, we need to turn it on, a DC motor, a 24 volts DC motor. Right? We need to turn it on, and it uses 10 amps. Can you connect that directly to the PLC? The answer is no. And what you would use is, let's say Y0 is right here, right? And your common is right here. Probably 24 volts DC to your common. Turn on a control relay. And the control relay has a set of contacts control relay has a set of contacts that is going to turn on 24 volts DC, 0 volts DC, and you're going to turn on the motor. And this contact is rated for, let's say, 12 amps. Give it a little bit more just in case. So you can provide that amount of current to the motor. All right? Please write down your questions over this slide. Take your time and write the questions on this side. On this slide that you have questions about, just write them down. The most important thing is that you understand syncing inputs and sourcing outputs, which are the ones to be used. But there'll be some questions regarding this and syncing output. So I don't think we discussed the syncing output. The syncing output, basically, you're connecting 0 volts DC to your common, and the PLC and the PLC would take the current from the device. Let's say this is a control relay with 24 volts on the other side. Basically 24 volts instead of 0 volts over here, or 24 volts over here, and over here you put 0 volts. So the current goes from here and syncs it to the PLC. Okay. Let me go over this real quick. So let's pick it up an input point. This is the common. And this is X1, X0 or X1, no matter. All right. So in order to configure a syncing configuration of my PLC I/O, how can I accomplish this? So take your time. You just gotta put a voltage here and a voltage here. So remember, syncing will take the current from the input device and sync it down to the PLC. I'm gonna give you 3 minutes. Okay? So syncing, remember the current flows from positive to negative. So this one has to be the positive voltage, and these have to be the 0 volts. When they say negative in DC, it's not really a negative, it's the common. So it will go from the higher voltage to the lower voltage, right? So 0 volts DC, and this one is 24 volts DC. Oh my God. Sorry. 24 volts DC. Now the current sinks into the I/O, goes through here, through the electronics inside the PLC, and goes back and finds its way to the common. Okay, that's on the input, right? Now, sourcing input. We're gonna do exactly the same thing. We're gonna have the common and X0. What voltage am I gonna put here? what voltage am I going to put here? This is your start button. All right. Should be evident now that in order to have sourcing, you want to source the voltage or the higher potential, or supply the current, you may say, to the device from the PLC, sourcing, right? So we'll go 24 volts DC on your common, and over here 0 volts DC. Okay. Syncing output device, or output module, actually, because what we're saying that it's syncing is the actual PLC, not the device. Syncing output module. Wiring. So now we're gonna have the common Y0, which is the output. Let's call this a little light, a red light. What voltage do I have to put in both terminals, A and terminal B? So just like the input module, right? So I'm syncing the current. So syncing, the current goes in the direction to the PLC. So this one has to be the positive, and this one has to be your common, your lower potential, right? Your 0 volts DC. Now sourcing output module, right? The red LED light. What voltage am I going to put over here? So I'm going to put 24 volts DC, right? And I'm going to supply the voltage. I'm going to source or supply. Source comes out of the PLC. Out of the PLC. Into the PLC. Okay, and over here you're going to put 0 volts DC. Okay, so now we have discussed what are the syncing and sourcing configurations for the modules.
Yay!
Okay. Going back to the syncing and sourcing, now you guys know that the input sensing, there's an input card or input module or input points, depending on the PLC. In our case, we don't have an actual input card. It's in the same PLC, right? So it'll be an input points inside the PLC. So notice that the current goes from the 24 volts over here. All right. If you were to draw this like we always do, just to find common ground, which is the same as this, but usually they draw it in a ladder style, right? You're gonna have 20 volts 20 volts DC, right? And over here, they're gonna put 0 volts DC. Why did they draw it like this? Because it's the same thing. Basically, what you're doing is this. You're putting a battery, a 24 volt DC battery, with a positive and the negative. The negative goes to the common. The negative vote goes to the common and the positive goes to the devices. So notice that goes from the positive and sinks down to the PLC. So it's not coming out, right? So based on what we just discussed, sourcing, no matter if it's input or output, right? Sourcing PLC module or PLC IO module, right? Current flows out of the device, right? Okay. Syncing PLC IO module, current flows into the device. Okay? So in this case, it flows into because the 24 volts is at this side, and the common, you're providing it with 0 volts DC. If we go back to what we just talked about, so notice that syncing 24 volts are over here, and they're sinking into the PLC. Sourcing 24 volts come out of the PLC. On the output as well. Syncing goes into the PLC. Sourcing, I'm sourcing the 24 volts. Or am I syncing the 24 volts? Or depends how you look at it, right? So now, discrete output connections. Okay. Notice that our PLC is going to be always wired like this. In our case, for our lab, for our purposes, our outputs are Y. Went through that. So what does our actual lab look like, right? So the design that we did, just like you guys have to, and this just to give you a hint for the project, this is how you're gonna wire it. Your I/O wiring gonna look like for your project, for your stoplight. The only thing that it won't have is control relay 1 and control relay 2. We will use some of the lights that are there, but just so you know, you almost have almost everything you need from the project. You have your start, your stop button. This black button is not used right now, not used. But we will use the forward and reverse for our little experiment that we will have today. Okay. Now notice that the outputs can only provide 0.5 amps of current per output at 24 volts DC. More than this will burn it. So if you have a load that needs more than 0.5 amps. Just to give you an example, 0.5 amps is a lot. Like for example, the example that one of the students gave about the thermostat and turning on the heater. Your heater does not run on 0.5 amps. So you have to have a relay. So using the output, let's say a Y, an output, you turn on the relay, a control relay, and use the contacts of the relay to provide the current needed to that device. Remember the little applications that we talked about on previous session? That is what we're going to use. Okay. Going back to the PowerPoint. Okay, this is an overview of the software. You guys can watch that. Let's jump into our first PLC project, right? So a machine builder has just installed a machine and it's a system integrator. This is you. The PLC programmer, installer, etc. PLC-based control system. The requirements are the requirements of the machine is to control a motor by having the following functions. This is going to be a DC motor. DC motor is going to have a normally open momentary system start. It's going to have a normally closed e-stop, a two-position selector switch, a momentary jog function. So the jog function, we're going to put it in X2. Only one motor, which is going to be, actually, we're going to use this as the black button. Only one motor can be active at a time. If not, the motor will be damaged. Okay? So the control relays is going to be a control relay 1 and control relay 2. You must design a control panel push button station similar to the one that we have on the lab. Do a wiring diagram and PLC program. Okay. Materials all the materials to be provided by the customer. You would only have to provide how much you would charge for these services. Assuming in your design that you will have two relays, right? We talked about this. Control relay 1, control relay 1, and control relay 2. One relay will be forward. Let's say this one is forward, this one is reverse. Okay? And we're going to use the Do More software to start programming. Okay? Write everything down. So here you go. Let's start by designing our push button station. So our push button station We're going to have a start, a stop, right? Then we're going to have a jog, and a selector switch, forward, reverse. Okay. And so we're going to leave it there. We're going to leave it there. Now we're going to do the I/O wiring, right? So the I/O wiring is going to look something like this. So for simplicity, you don't have to draw the green, red, blue, and orange lights. So this starts for green. This stands for red. And this stands for orange. Okay. You will have to draw X0, X1, X. Actually, we said that this one was not going to be used. We will use it. It will be our jog button, and our selector switch, which one of the selection goes to X3. If that one's not selected, it automatically defaults to reverse. It's a little bit different than last time. And this is going to be our motor circuit. I'm going to apply 24 volts DC. We say it's 24 volts DC. It's 5 amps. Remember, this is why our output can only use 0.5 amps on the PLC. So we use control relays to provide more amps. So this can provide 5 amps to that motor. So when it's forward, let me change the color here. When it's forward, I'm going to use green as forward. When it's forward, control relay is going to turn on. Control relay 1 is going to turn on. So this one turns on. This one turns on. So the green over here in the positive, over here in the negative. While at the same time, notice immediately that control relay 2 is not on. Control relay 2 is not on. Okay? So 24 volts goes to the positive, 0 volts DC goes to the negative, and the motor will run this way, right? Say clockwise. Now, in the program, going back to the program, when control relay 1 is on, control relay 2 cannot be on, right? So now when it goes reverse, control 2 turns off, and now control relay 2 turns on, and now immediately you can see how now the positive side, the positive supply, goes to the negative, and the 0 volts goes to the positive. And this will cause the motor to turn backwards. Okay? So now we have to create the PLC program to do this. Okay? You have to create the PLC program to do this. So we have the push button station, right? Just so you guys see it. The start is going to be green. The stop's going to be red. You guys already know that. Now, we're going to start doing the program, okay? I'm going to put the program in another video so you guys can see it better. I hope you take notes. Replay this video one more time so we can go through it.